Today we're looking at the NexCell V2.8 lithium hardware. This is going to be a long video just like the last one. I am going to be moving pretty quick in this video and there's not going to be any show and tell. If you need to reproduce something, you can do that on your own end. I'm giving you all of the information. I've tested it. I have the equipment to do that. I don't have time to explain all of that. If there's anything in particular, I could maybe do follow-up videos, but I'm going to lay out some ground rules here. In my last video, there ended up being a lot of ad hominem attacks with some of the community members who are on what I'm calling Team Jack. And I simply will not reply and engage with those ad hominem attacks. At best, I'm going to reply with, I will not engage with ad hominem attacks. I might add a quip on there just because it's the internet. Second thing, ground rule, if you don't understand science or you don't want to understand science, this video is not for you. This is a factual analysis of a product, and of course, yes, it is my potential competitor's product, but that's not why I'm doing the video. I'm doing it because of safety. This is a safety issue. There are many safety issues, and unfortunately, I don't have a lot of good news today either, so there's a spoiler there. So who am I? Just very briefly, I say this in any of these videos that tend to be controversial. I'm an electrical engineer. I have a BSEE in electrical engineering. I've been practicing electrical engineering since I got that. My whole life I've been a nerd. So anyway, that's who I am. If you want to know more about who I am, watch the previous videos. Don't have time for it today. Again, why am I doing this? Safety. Do I feel bad for Jack? Yes, of course I do. This was Jack's dream, and I totally get that. But he failed to procure the requisite engineering knowledge to make a safe product. And we're going to look into more reasons why today. I've already done two pretty extensive videos, of course, on the V1 hardware. So here was the V1 hardware. This is a taken apart one. And then, of course, here's the V3 that we're looking at. I've already taken one apart. But this is just my prop for the beginning there. So yeah, what is NexCell? NexCell is an aftermarket lithium conversion for nickel metal hydride Toyota vehicles. It's basically these, a certain number of these, depending on which vehicle you have. And there are pretty severe engineering deficiencies in these modules, as I've addressed previously. And as you'll see today, there's nothing really new here. So first of all, very quickly, I want to talk about as received packaging. This is not a portion of the box that I received. This is to show you how you properly ship lithium batteries by themselves. They're UN 3480 class 9 hazardous goods. So if your box that you received doesn't have these materials on it, then it doesn't necessarily have to be FedEx, of course. If you ship FedEx, you have to use these that have to be printed. Of course, these aren't filled out. This is just a prop I made real quick here. You need this logo on there, 4x4 inches, twice on the box. It has to be on the same side as this stuff, and then also in one other side that people are likely to see it. So basically not the bottom. If your package that you're shipping for these NexCell modules does not have this on it, then it's not being shipped legally. It's actually a felony in the United States to not follow these guidelines. And I will say that the package that I received, which was as packaged by NexCell, did not have any of this. It was completely unmarked. So anyway, the point is you don't want airplanes catching fire. I have a whole video on this. If you want like a 20-minute video showing you exactly how to do that, don't have time for it today. So next up, the visual differences between the V1 and the V2.8. We're going to start with everything except for the circuit board. The circuit boards are, of course, different. So let's look at them. I've taken them apart. We're going to look at the cases first. So the V1 is the one that I looked at before. The big difference is that we have some cooling holes. I think we all knew about that already. The design's improved a little bit. Otherwise, it's essentially the same. I did notice that the V1 had some foam pads in the bottom and the V2.8 does not. I think that's because the cells are slightly larger. We'll look at that next. Otherwise, essentially it's the same mechanicals. I still had a lot of feedback. All my feedback from the old video about the enclosures persists, but there is better airflow there. Oh, I did note the PCB is mounted better. So in the V1, the PCB is just stuffed down in the bottom. So here's a V1 module where the PCB is just stuffed down there. Kind of weird, kind of crazy to get it out of there. In the V2.8 here, it actually clips into the top. That's the wrong one, let's see. Sure. I of course have plenty of these. I think it goes like this. It doesn't matter if it's one way or the other, but it actually snaps into the, yeah, it goes like that. It actually snaps into the top. So it's actually better secured there. There's still some issues where when the top cover is assembled, this is a V2.8 module. These BMS wires are still kind of rubbing, and I don't like that. There is, of course, heat shrink here, but it's not guaranteed that. Anyway, my other issues persist. So again, if you haven't watched the V1 video, you should watch it. I don't have time to go through all of that. We're gonna be focusing on the PCB today, so I just wanna get to that as soon as I can. So yeah, larger cell capacity. The V2.8 is 3,500 milliamp hours. The V1, here's a V1 that I removed. This is from a custom RMA pack. These were 3,300 milliamp hours, so 3,300 versus 3,500, so a slightly larger cell. I did notice this was very difficult to remove, and it's because all of these cells are inflated. So every single one of these cells has failed the. Anyway, we've had a vapor decomposition inside of here from the electrolyte, and that's what I like to joke it. Anyway, let's see, that is larger cell capacity, the new PCB. Yeah, so we have the new PCBs, and again, we'll look at this in more detail here for most of this video. So this is the V1 PCB that I reviewed several months back. This is the V2.8. When I'm saying V2.8, it's what's printed on the circuit board right here. I got some complaints last time that I didn't show a close-up of this, so here's your close-up if you want to pause it and look at what I'm looking at, which is silliness. This circuit is functionally identical, and we'll look at that later here. So yeah, PCBs are different. Otherwise, anything that I haven't mentioned here is basically the same. You know, I probably forgot a couple of things, but everything I noted, all the issues, all the major issues I noted in the last video, they persist. And one of the crazy things is that this V1 was first released, or sorry, this was designed rather on 2020, March 27th, and the V8 is 2023, May 15th. So more than 3 years. 3 years and almost 2 months later, we have effectively the exact same deficient design. So that is representative of the engineering capabilities. All of these improvements, I don't actually know the numbering. The numbering seems to kind of really jump around. I thought we were on 2.5, but apparently we're on 2.8. And of course, there's this promised version 3, which, you know, when it comes out, I'll review it. Hopefully it's good. You know, man, people think I'm out here to destroy Jack and his business. And I get that this could do that. That it's already happening. Like, Jack has already done that to himself. But again, my focus here is safety. So there are safety deficiencies. We will look at them. Yes, so let's look at the high-level electrical differences. As I stated before, the V1 and the V2.8 PCBs are essentially identical. And we will look at the differences in more detail, but at a high level, the V1 turned on at a pretty high state of charge. So the balancing basically started, you know, above 99% state of charge. This is an approximate SOC. I did not characterize the new cell. So the 3,500 milliamp hour cell, I just got these this afternoon. So I haven't characterized the cell. I of course will. I literally just looked online and figured out approximate resting VOC to SOC conversions. The old BMS basically never turned on. It only turned on when a cell was overcharged, essentially. The new one turns on to 70%. One of the side effects of this is that when you leave your car sitting, if it is charged over 70% when you start it, or I'm sorry, when you turn the key off, when you come back in, you know, infinite amount of time later or whatever, you know, weeks later or days later, well, you can do the math, it's going to be at 70%. That's when the circuit disables there. Approximately, this could be 75, 80, 65, 80, you know, these are very relative. The point is that the V1 SOC stuff only kicked in, I'm sorry, the V1 balancing circuitry only kicked in when the cell was overcharged, and it just took it to where it wasn't overcharged anymore. There are issues with bringing this down to 70%. One, there is some uncertainty in where this enable is. This is still right on the knee of where the resting cell voltage of LFP cells are. But we're actually starting to get down into the flat section, the low slope section of LFP. So LFP cells are very, very flat throughout their you know, charge discharge. This would be a discharge. Previously, we were kind of like, you know, enabling if it was above there. I know I have the x-axis backwards. That's fine. This would be empty on a discharge here. And now we've moved it to where we're just kind of right here, higher on the knee. So this can actually make the cells more unbalanced if the uncertainty is, you know, if these aren't tight tolerant parts, which I don't see that they are. But I think I saw 1.5% at one point, which is pretty large for the voltage range that we're looking at. We'll look at that in more detail. So the approximate cell voltage when the cell balance circuit is fully engaged. On the V1, it engaged very, very quickly and cleanly, and it was at about 3.53 volts. So again, greater than 99% state of charge, we were fully on. And that's the difference between, you know, when the MOSFET is in an active region versus saturation. The new cell is fully engaged at 3.315 volts, which is about 90%. And there's actually an interesting unstable region between approximately 70 and approximately 90% on this new design that wasn't there before. It was always stable, and we'll talk more about what I mean about always stable versus, you know, oscillating in a second here. I don't think that this is actually going to cause any impact, etc., but it will mean that as the cell gets closer to 70%, it's going to discharge slower and slower and slower. I'm not sure if Jack meant to actually make an oscillator on this circuit. I don't think he did, but he has. There's an instability. It's a bistable oscillator there between a region. We'll look at it. Don't need to get too much into that detail there. So there are several variants of these PCBs. All of the ones that I received are the same actual circuit board, same revisions, so they're all 2023 May 15. But they do have different BOM populations, different part populations, and it's only in one specific part of the circuit, which we'll look at later. I will note this is on the module with the red dot, which from what I understand is where the service disconnect goes. So if you look at the modules with the red dot, there's terminals on both sides. So terminals on both sides, that's where that service disconnect goes. And this wire basically gives this one PCB its isolation when you remove that service disconnect. And the way Jack is doing that is not very safe, and I will show you that here. I'll describe it to you. Anyone can verify it with a caliper or even a millimeter measure. So if you look at the normal module here, I've taped over that one there. I've got some personally identifying information that I've promised my sender I won't reveal. So this wire basically, Jack drills out this hole. So this isn't for all of the modules except for the one with the service disconnect. And this is the one with the service disconnect where you drill out the hole. There was less than 1 millimeter of clearance here. And in a condition when the service disconnect would keep you alive, you're gonna have the entire pack voltage, HVDC plus and minus, whichever side they're on, spanning that less than 1 millimeter gap. And of course, since this is probably hand drilled, it looks very hand drilled. There's no guarantee, there could be metal bits or whatever. I have not seen that, but that is certainly a risk you run when you have a manufacturing step like this. If you wanna do this safely, you probably want a part BOM depopulation, where you literally remove a large enough component that there is a guaranteed gap. Typically you'd want probably 5 millimeters, at the minimum probably 3 millimeters for something like this that's user or installer serviceable part. In an assembly line, a serviceable part, you might want like 5 millimeters there, but 3 millimeters certainly would be the minimum you would want. Again, I saw less than 1 millimeter here. That's the only schematic difference on the circuit board. Otherwise it's just part changes, and we'll look at what those are again, as I mentioned. So let's get the board I actually tested here. So yeah, high level here, we'll come and revisit some of those things. So next up, I want to talk about reverse engineering the schematic. So this is essentially 5 of the same thing. There's no inner IC that's actually looking and comparing anything. There's no computer. Just like the V1, where we had these 5 discrete elements with essentially no interaction with each other, we have the same thing here on the V2.8. It looks like there might be something more going on, but it's literally just because this is where the cell 1 plus to 2 minus, and then 3 plus to 4 minus or whatever are. So at 1, 2, 3, 4, 5. I did notice the nice tacked on resistors here. We needed to balance these just 20% faster rather. We need to balance 20% faster, so we put another 82 ohm resistor there. This works out to about 14 ohms per channel. I have 13.7 here mathematically. Okay, so yeah, this was my first kind of attempt. Just I didn't know what anything was. Here was my second attempt. I'm just kind of fly through this. I'll point out here while I have this. This is where we're setting a reference on this new circuit. I haven't described it, of course. These are the only components that have changed between the several boards that I've looked at. So I have more boards than this, but I've just grabbed a sample. I did look at a bunch. But yeah, these parts here changed, and it literally just sets like a trigger threshold on when we actually enable the main part of the circuit. So done with that. Here's the actual circuit. So I should keep that though. So 8B to 8C was a simplification. So if you look here, we have an open drain, and it's going through these discharge resistors here. So these are those discharge resistors, and then all of them, it's just repeated 5 times. And then one of these here is the MOSFET N12. That's actually N12 right there. I will note that I actually, the circuit I tested, sorry, it was actually this board here. The C10 was broken off on this one. This is just across the MOSFET gate to the source, just to keep noise from turning that thing on. It was broken on here, so I didn't test that channel. It still behaved the same. I did actually test it, but it's not what I drew my conclusions from. So C10 here was missing. I did flag that. That's just a quality issue there. You hopefully would have a test to determine when a part is missing, but there aren't even any test points on here. So yeah, so we tested this guy, and I also tested that one. So essentially everything else here can be summarized into a magic black box. And this magic black box is essentially N10 here, plus N11 there, and then all of those other parts there. But again, we're gonna just say it's a magic black box because ultimately it doesn't really matter what it does. I will explain what it does in a minute, but first we're gonna look at what this achieves. So does this achieve communication with the OEM computer in any way? No, absolutely not. Does this spoof the voltage output from the cell to the actual existing BSU in the Prius? No, it does not. It does none of those things. And so a question is, Jack had this unplugged connector theory for the battery meltdown in the my NexCell Lithium pack caught on fire post. I think that's the title. His initial theory, which has already been thoroughly debunked, just conceptually, is now totally debunked having looked at this. There's no way an unplugged BMS connector would cause that pack to melt. At least not all at once. Now, if that had been unplugged for a long time, and the pack wasn't able to balance, and the other ones were getting discharged to 70% here, then a disconnected connector could cause that other one to stay, fully charged, where the other ones are always getting bled down to 70%. And now you have a pack imbalance that's actually introduced by the thing that's trying to balance the pack because the connector wasn't plugged in. That's the only case where the unplugged connector would cause the pack, that specific module, to overcharge because the other ones are getting discharged to 70% and this one is staying at 80 or 90 or whatever. It's staying at whatever the other ones are plus some percentage, and then it overcharges. But in normal use, that having a connector unplugged should assert a fault condition because things like this SIL level 2 thing should fail safely. And that's not the case. So if the connector being unplugged was the issue, it's not because the circuit wasn't able to inform the vehicle. The same can, put another way, if that connector were plugged in and the cell were actually broken, rather than just balanced, whereas other ones weren't balanced because the circuit wasn't plugged in, we couldn't detect that. So a cell actually failing would cause the same failure condition, the pack to smoke. Hopefully some other engineer can back me up on that, but that's, I'm not even sure you could contest that, although, man, based on the lowest common denominator that I've been arguing with today, I'm sure that people will argue about that, and I leave it to the community to reproduce that statement here. And again, as I mentioned on the forums, if anyone wants, I can send you modules that I have prepared into a condition that will almost immediately fail if you were to break regen. Discharging 4 of the cells in a module and then overcharging 1 of them and then driving the car. That's gonna, anyway. Anyone who wants to take me up on that offer, I'm serious, I will do it. In fact, at the end of this, I'm probably gonna just give this entire pack away and give a very strong caution to whomever takes it for free. I will literally, if you pick it up, or if you pay for me to ship it to you, you can have it. I don't want this. So anyway, a little bit off topic there. So electrical differences, yes. Schematic reverse engineering. Let's get back to this guy. We have the magic black box I mentioned. This magic black box is N10 plus N11 plus all of its effectual circuitry. This is essentially identical to V1. Even though there's more parts, It's essentially identical. It's slightly different because in the V1 we blah blah blah. In the V2 we have an extra. I think there's a PNP. It doesn't really matter. I didn't even look at it. And then we have another voltage reference. I might have those backwards. It really doesn't matter. I looked at the circuit on an oscilloscope. Identified a condition that we'll talk about here when it's not fully in saturation. Let's ignore that for now. So what do we have? Here I've just hypothetically looked at the 5th cell in this module, the most positive cell in the module, and the 4th cell in the module, the next most positive cell. And we have this open drain in FET here with a 13.7 ohm resistor. So when this is enabled, you know, it's pulling some amount of power, and we'll look at that in a minute. Here's that uncertainty range, and actually I think I continued this later. I have roughly planned these videos, but you know, the production quality is not something I care about. I'm trying to get the technical content across. So that is the essential schematic reverse engineering here. We are literally doing the exact same thing, and that is that we are discharging cells that are over a certain percentage of state of charge. Specifically, we are not telling the computer, or there is no computer, we're not adding anything. We're not telling anything anywhere when anything bad is happening. So we still have all those failure conditions if a cell fails, or a cell fails because the connectors unplug, or whatever. We don't actually have the supervisory control method of telling the car something is wrong. And that's a big issue there. So we also don't have any over voltage protection or any kind of way to alert if a cell is over voltage. That's kind of the same thing. But yeah, basically all of the issues in V1 persist in V2.8, you know, 2 years and 2 months, 3 years, was it 2 years or 3 years? 3 years and 2 months later, from the V1, which is 2020 March, to the V2.8, which is 2023 May. Yeah, anyway. So let's see what's next. We have a cell balance meltdown condition that I'll talk about in a second. Of course, we still don't have any kind of fusing or fusible link. These wires are still pretty beefy to where they are gonna probably sustain a burn for a little bit because they are a little thick there. They're not crazy. There might be 22 gauge, 20 gauge. But it'd be nice to at least see fusible traces on here. Don't see that. So, you know, again, it's the lack of supervisory control. The lack that we can't tell the car when to stop. And I will talk about some proposed solutions here in a second. So first of all, let's look at some data. Because apparently using open source spreadsheet things is something that people doubt. Like, what? Head was rolling on the floor there. I don't understand. I've decided to do it all by hand, just cause, whatever, right? Let's knock it out. If you can't trust the program, and obviously you don't trust me, so, you know, I'll let you do the math. If you don't know simple V equals IR and, you know, I squared R and V squared over R, if you don't know that intro stuff, again, why are you even watching this video? I leave it to the community to distill the technical content in this into the safety warning, into the 1 minute video or the 1 paragraph text write-up. That's not what I'm doing this for. I'm trying to inform the safety conscious people in this community that there is a safety issue. And initially it was Jack, but you know, we don't talk anymore. So yes, let's look at 9C. That was the cell deficiency, cell balance meltdown condition. So let's look at what happens here. We have, I basically ramped the voltage on this cell to just insanely high values just to prove a point. And then I looked at the actual balance current, so how much we were discharging the cell that was connected. Of course, I had test equipment, not a cell hooked up. And then this would have been the MOSFET plus discharge resistor power here. That's why I did this like that. So this is here, how much power is going through this pair right here. And then the next one is the ESR of the FET plus the R balance. That's simply V over I there, and then we get that. And then I have FET ESR. So the FET effective series resistance was literally this value minus 14 ohms, because that's what it is, you know, 13.7 ohms. And then I have the FET power here. The FET here that is discharging is, I believe, that one. It's N12, yeah, so it's this one right here, or that one, or this one, or that one. They're all the same. And this resistor here actually syncs up to 200 milliwatts when we get into this enable condition where it's not in saturation. So 200 milliwatts on a SOT23 is actually quite a bit of delta change that can happen. Typically a SOT23 might be like a, you know, a theta JA of 500 degrees C per watt or whatever. So 200 milliwatts could be 100 degrees C delta over whatever the ambient temperature is. In this case, that's not actually what's happening because there is a this capacitor here on the one I actually tested and then also some other stuff, I think just some fortunate coincidences that keeps most of the power in here. But we do spend a lot of our time in the active region and not in saturation. So in the active region, this is an ohmic, a resistive thing, and it has up to 159 ohms of ESR, so it's not fully on, and then of course later it's fully on. Again, if this data doesn't make sense to you, like, I get it. Hopefully someone can distill it. I'm not going to. This is data for your liking if you like it. If you don't like data, fine. So 9E was this unstable oscillator window. I've mentioned this a few times now. When we are from 0 to 3.293 volts, the discharge resistors are off, so they're not pulling any current, or not any appreciable current. At 2.93 volts up to 3.307 volts, it's a small window when you look at it here, but when you look at it as a function of state of charge, it actually does get a little bit bigger. We get this bistable oscillator effect. It's most easily measured on, in 11, the top pin on N11 here. People made fun of this pointer, but here, that's N11. This is why I use it. The top pin on this SOT23, there we go. The top one right there. If you measure that with an oscilloscope where your negative reference is here, then you will see the oscillator behavior that I see there that I just described. And so while this persists, again, the MOSFET itself is doing most of the power sinking, and the resistors themselves are doing quite a bit less. Once we get above 3.307 volts, our FET is fully saturated, and you can see that the effective ESR drops to 0. Of course, it's not 0. Someone's going to call me out for that or whatever. It's hundreds of milliohms or whatever. Seriously, pick topics that you can actually defend. So one thing here, let's look at the power here. In real world conditions, let's say 3.695 volts on a cell, we're sinking about 1 watt. And these can handle that. We've got, it's 6 in parallel here. There's 5 footprints, but there's a dead bug on every one that gives us a 6th one. I will note that putting this one on here only changes resistance. It does not increase the amount of power that you can sink because there's no additional thermal mass. There's no copper traces or heatsink or whatever to pull that power out. So for some reason, instead of, if we wanted, the 14 or 15 ohms here, we could have just done, a 75 ohm resistor instead. We could have changed all of these to 75. Well, instead we hand populated an 82. Maybe this was an early one and just had to be done. I get it. Maybe it's a 75 now. Anyway, yeah, up to 1 watt, this can totally handle that. The condition I was getting at where we don't have any, we have a cell balance meltdown basically at high voltages. If one of the cells fails in this pack, then its ESR is going to get a lot higher, and therefore the voltage across this circuit, which can't disconnect from the cell, is going to get higher as well. The worst case condition, of course, this would just fuse immediately because you get the whole pack voltage, 200 volts, 250 volts. The trace, everything will just stop existing. But if your cell is just starting to fail and is at bumping up to 4, 5, 6, very unsafe things, you might have already released the magic smoke. But you can look here that we very quickly ramp up, 2.6 watts, 3.6, 7.4, and then I did 30 watts very, very briefly. These can't handle that. So just for reference, this is a 2512 resistor. They can handle 2 watts with a 300 millimeters squared surface area of copper trace per resistor. So that's this is drawn to scale here. We of course don't have that. I would imagine, so typically you wanted to rate these to half of their rated value, and typically a 2512 is rated between 1 and 2 watts with this here, but this doesn't have it. We're talking maybe a 1/4 watt continuous per here that we could get. So we're looking at, with 5, again, we don't have 6, even though there's 6 physical resistors, we only have 5 from a cooling stance. So we're talking about maybe 1 1/4, 1.5 watts would be where you'd want to be. And under normal operating conditions, that's kind of right where we are. This is 1 watt, 1072 milliwatts or whatever. And so that's, we were designed there, but again, there's no way to disconnect it when it becomes full. There's no way to alert the car to stop charging. And so we do need to have some design in here to where instead of these things becoming fireballs because they're sinking 5 watts a piece or whatever. So that is that. Yeah, so again, no under or over voltage protection. There's no way to alert the system. All of this V1 defects are here. This circuit is functionally identical. There is nothing else besides this open drain MOSFET here. It's literally a switch. You can turn it on, you can turn it off. You don't have any other signals you can tell anyone. And so, the magic black box, I mentioned when we get back to it, I didn't even draw it on here. It doesn't even matter because all of this stuff is behind that gate driver. The only output is that. So anyway, that's this. And of course I tested this on thing. I brought the one channel all the way up to 20 volts. Yeah, 20 volts. So didn't see anything there that I liked. Okay, so how would I do it? That, you know, people, how come you want help, Jack? You know, he's my competitor, obviously, but here, let's do it. This is not an answer. This is a very high level thing. So the first one we're going to look at is how I would do it with the existing design. And what does that mean? With the existing design, it means we don't add any new connectors. So we still hook up the battery sense tap that goes to the BSU, still hooks up to the same spot. And then we still use the, you know, this circuit board space in there. That's the constraint I'm giving myself because I imagine that's probably one of Jack's design deliverables. And you know what? Maybe this is his V3 when it comes out. You know, that'd be cool. So let's look at it. What is the minimum safe design without a central CPU? So this is not a recommended design. I don't recommend this design, but given the design constraints I just laid out, what would I do? Each individual cell would have Jack's V1 design. So that's this guy right here, which was plenty sufficient to balance when it needed to. You know, that's fine. I don't like it. It could be done safely. Next up, we need a V cell high and low threshold comparator. And so what this does is it literally outputs, it sends a high signal if the cell voltage is not in the safe range. So, you know, 3.8 on the high end, you know, really 3.65. The thing though that is with this, without a central computer, this threshold comparator, when it fired, would assert a check engine light. But you want that in a safety condition. So, you know, you don't want to pick 3.5 volts because of the stated range of LFP, but maybe you pick 3.7 volts or 3.8 volts on the high end. On the low end, you know, same magic, 2.5 volts or whatever, you know, whatever, something low, 2.4. And it output enables, so it goes high if the cell voltage is bad. This is the safety thing. This is what the battery management system should do. When the cell is unhappy, typically because it's hot, over or undercharged, or it's just really worn out compared to everyone else, you need to tell someone about it. You don't, anyway. And then we OR these all together. So the same PCB has the V1 design here, which could be done much tighter. You wouldn't even need, you know, these 2512s. I don't even typically recommend 2512s in automotive because they're much more likely to crack. So 1206, 1210, you know. But whatever, here we are with 2512. So yeah, we do all 5 other cells. Now, of course, we will need some isolation logic here because, you know, we have these voltages here. So this could be, you know, an opto isolator or, you know, a 5-channel opto isolator or whatever. And then we have our module positive coming here with a pull up of some kind. So Jack's signal soother circuit. Basically proved that we can build some kind of op amp thing here. You know, this is just a conceptual one. I've just got to pull down. And when any of our cells or all of them, you know, it's an OR gate. So when one or more cells asserts, we basically pull the module positive to ground, to the pack negative. And that will tell the BSU using the existing wire harness. It'll basically tell it that it's at 0 volts, or you could make it do any voltage. You know, if you added a voltage divider here, you know, you put a resistor there, you could make that assert 10 volts or 20 volts or, you know, something to where something safe happens. And of course, you're not actually shorting the positive because you do actually, I said you don't add any new connectors here, but I mean, honestly, you need to add something. And we're gonna add a single connector, and it's basically another stud, and you hook your BMS sense lead to that stud instead. You got plenty of room inside of this case here. Let me grab the another V2.8. Oh, I need to grab one with the modules in it here. Somehow I don't actually have one right now. Here we go. Yes. So here's a V2.8. And all of the space under this is empty. There's no cell here. There's just some rubber pads, which, you know, I commented previously how silly that was. That hasn't changed. So you have these rubber pads. Ideally, you would fix the issue where you're not actually compressing a polymer cell. But, you know, you have room in here where you could add another terminal and as much circuit board as you needed. And what does this third pin that you hook the BMS wire up to do? Here's our third pin that we've added or whatever. That allows us to spoof voltages when bad things are happening so that you can use the OEM BSU, the original computer there. It's not an elegant solution. And again, you need to make it only assert when something is actually going bad, because you don't want to false alarm your customers, because then they'll get used to it, and when the alarm does occur, they won't do anything. So we have this per module vSense connection to the OEM harness. Again, that was this. So anyway, that is what I would call the minimum safe design. I don't recommend that design, however. What would I do? What's the ideal solution here? I would do what everyone else does, including me. You know, basically, I would take, this is LIBCM, I mentioned it before. Man, I know a couple of y'all don't care about this. I do. I know there are people who do. I'm going to show it to you because, hey, look, it already exists. Doesn't exist for the Prius, but actually I will be using a version of this as is in the Prius, because this hardware just implicitly supports the conceptual replacement BSU, the LI-BSU. The version I make will of course be much smaller, because there's a much smaller room in the Prius, and also because if these are distributed, as I'll talk about next, you won't need them all on here. You will just have a core logic section. So you'll have a core logic section, some part of that goes inside of the OEM BSU case. And that's of course the LI-BSU project that I'll be working on. It has what's called an ISO SPI bus. Just look it up. It is a fully galvanically isolated electrical communication interface. It's specifically designed for battery management, or at least originally was. It's used for lots of things now. This is a 2-wire, no external power required. You literally have a pulse transformer, an isolation transformer inside. You'd ideally want it on both sides so that the external user signals aren't energized to the pack voltage. So you'd have the same isolation transformer on both sides of every cell. And you literally have an ISO SPI. So there's this ISO SPI channel, and the LTC parts at least have a cascading ISO SPI. So with no additional hardware, you need one 6820 part here, and then you can do your 6-channel. The 12 channels, the LTC 6804, I'm very familiar with it. There is a 6-channel version of it, and probably an 8, and probably a 18. I know there's an 18, it's the 68, 18, I think, whatever. But anyway, get yourself a 6-channel, fully isolated BMS system here. Now we can fully talk to it. We can literally get every single cell voltage. We can get temperatures. This has a ton of ATCs. It can measure temperature sensors. It could measure current sensors if for some reason you want to do that. It can do it all. And that's this here. So 12 channels takes up this much space on the board. Here's 12 channels again. So here's a 12-channel thing here. It has balance resistors. It has balanced MOSFETs. You don't even need the balanced MOSFETs, although I do highly recommend them. You can actually use these internal ones, but you have to really be careful about not overheating the die. And when I'm balancing, I just want to balance. But you could make this smaller. This is a tight layout, but again, you could use 1206s, because once you have a centralized battery management unit, you don't really need to manage the battery that much, because like, you're not doing it in a dumb way. You're literally doing it all the time when the car's off. Anyway, so that's basically what this is. You take this board and you make one component here that's the main one, that's the LI-BSU replacement computer, and then every module has one of these. So here's 1, 2, 3. You can see that it will fit on this board, or a slightly larger one. You have plenty of room in here to do it. So anyway, that's how I would do it. There have been a couple of accusations, again, by some of our lowest common denominator. I don't know why I stooped down to it, but there have been a couple accusations that I'm reverse engineering Jack's stuff to glean useful information. And as you can probably surmise from what I have said here, that there's nothing to glean. There is no intellectual property here. I'm beyond words that after 3 years, maybe there was an initial 1 or 18-month delay where these just weren't failing because the cells were still good. But, certainly for the last 18 months, like Jack's known this is an issue and has not addressed it in a way, or really hasn't even publicly acknowledged it. There's a lot of private talk, of course. I've mentioned that. I don't want to go totally down that rabbit hole, but I mean, that's it. The 2.8 hardware it's just not good. I don't recommend it. It's still not safe. Yeah, that's basically it. Like, I mean, what else do you say? I mean, I guess I can show my face. It probably looks pretty weird turned upside down. I don't know why that was such a topic of discussion. Don't show your face. Oh, the internet is a crazy place. So yeah, design deficiencies, again, summary, no over-under voltage protection alert. Same issues as V1, cell balance, meltdown stuff, there's no fuse. We have this unstable oscillation window that wasn't there before. Guys, this is a bad product. There's really no way to sugarcoat that at all. It's not a good design. The battery is not good. I have my previous test data on that. As I stated at the time, this is maybe 3 or 4 months ago, the V1 cell is the worst performing cell from any hybrid or electric vehicle that I've ever tested, period. So that, I have all the data to back that up too. So if you want that, it's on GitHub. I've posted it before. I, of course, post links if people ask for it. Yeah, you know, when Jack initially approached me, you know, it was very exciting, you know, hey, come help us fix our thing or whatever. And then, oh, I can't tell you anything about it. I can't send you one. I can't show you the schematics. I think that might have been a pride thing. Maybe I'm talking to the expert and I know he's going to grill me on it. And so then I procured my own, my V1 cell. You know, I got a couple or a few of them rather. I think, yeah, I got 3. And it was bad. And I told Jack it was bad. And that's what an engineering consultant does. Could I have done it in a more human way? Obviously. But I didn't. That's besides the point. So what? You know, maybe I'm an asshole. That doesn't detract from the facts here. And the facts are, this is a bad product. And I don't recommend anyone buy it. And you know, I would also recommend that anyone who has it installed, uninstall it and go back to nickel metal hydride. There's this whole discussion about, oh, Mutter just wants to sell his own product or whatever. I mean, wouldn't anyone doing a commercial thing, like, you know, of course I don't have the product yet. If I had the product today, it would be just a, hey, buy my product or whatever. But again, there's such a difference here, whereas my mantra is information wants to be free. I'm going to tell you how everything works. If you want to make it yourself, go right ahead. If Jack wants to make this and use it with his NexCell modules, that's fine. But of course, once LIBSU exists, this has half the energy density as an NMC cell. And yes, NMC cells are dangerous. NMC cells are dangerous if you don't have a battery management system. Jack always leaves the latter part of that sentence off. There's a reason why most electric vehicles use NMC, and that's that energy density. Why would you have in 100 kilograms what you can do in 50? You know, it's just, I don't know, it's wild. So yeah, of course, I'm not building my own battery. I think it's silly that anyone decided to. That you can't compete with LG Chem. You can't compete with Samsung SDI. You can't compete with any BYD, any of the, there's 5 companies that make, you know, 99.9% of all of the reputable lithium batteries in the world. Why would I think I could come in and build a cleaner, better performing cell? No, of course, wow, like what? It's a very odd choice. Get an off-the-shelf battery from anything else that fits. There are so many electric vehicles that have batteries, so many donor vehicles. And I get it, the Prius. So I'm coming from the field of the Honda Insight, where there were only 16,000, 17,000 of them sold. You know, and it's a smaller pool. I can assure you, I can assure you I have access to a near limitless supply of secondhand lithium modules, where if there is anything wrong with it, LIBSU, which this is not, this is LIBCM, my existing product, will just tell you, like, cell 47 is bad, replace cell 47, replace cell 71, etc. I'm trying to decide if I have any closing thoughts here, really. Yeah, so I am posting this video. Again, I've been working on this. I received these modules this afternoon. I've been doing a lot of forehand. It might sound like this is a very scatterbrained video, but I can guarantee you if I had unboxed and recorded this while I was doing it, like I did with, I believe, the V1, this video would be 10 hours long. So I did actually prepare a little, this is not a professional video as far as presentation skill. I could spend another day and make that. I'm not going to. Honestly, if your feedback is that the video quality is bad, or that I'm only showing my hands, or that I have this pointer, I have a great story on this pointer, but again, I know that people who call that out don't care. So Anyway, yeah, do I have closing thoughts? The only thing I have to say is that I'm going to be posting this video. It is somewhere around maybe 4 o'clock in the morning right now. Let's see. No, it's only 2 o'clock. Man, I got plenty of time. So I'm leaving on a trip tomorrow morning, early, and I haven't even started packing yet. I haven't done any of those things. So tomorrow, I am going to post this video tonight. It's unedited. I am going to then be traveling all day. And so all the comments and whatnot, have fun, knock yourself out. You want to ad hominem, all day long, go for it. When I arrive at my destination, I will probably go to sleep. And then on the next day, whatever that is, Saturday? Friday. Yes, so then on Friday, I will be looking and responding to questions. So don't feel like you need to jump in all at once, because it will be probably 36 hours from the time this video goes live to when I reply to anything anyone writes. So if anyone wants to chime in and just kind of confirm or deny the things that I've said, you could do that by just looking at your module if you want to pull one out and kind of just verifying the thing, that, hey, look, it's this. Oh, maybe you have a newer date. You have a newer date? Awesome. Send it to me. I'll pay you money. Yes, travel plans. I'm a little shot here. Thanks for watching. Yes.